Guys, any questions or concerns before we get started? No? Okay, good. All right, I don't think it's affecting you guys much, but I'm struggling with the videos, getting them edited and loaded. I'm not sure what the problem is, but so I'm going to continue to video this in the hopes that I get recordings of everything. But I didn't get Tuesday's lecture uploaded. It's I've got to combine, several of the GoPro files together, and I'm cropping out everything except what is, just the board. And when I'm rendering it, it's taking 3 hours, and then I get like 30 seconds of video and then a bunch of nothingness. I haven't figured out what that issue is, but with 3-hour iterations between, fixing something and then running it again, it's been a little hard to get anything loaded because then I have to sit there and wait 3 hours before I find out whether the fix worked or not. So that's exactly the kind of frustration that you can get into with FEA, is that you got this giant model and you tweak it and then run it and then discover 3 hours later that, that didn't work, so start again. So anyway, so it's kind of similar to what you can run into when you're dealing with some of these big models in the industry. So I want to talk a little bit more about element types today, and then I have assignment 3 for you, and assignment 3 will be using Solidworks. So we'll talk in general terms about how we're going to set that up and start using Solidworks. Okay. All right. So we were doing springs on Tuesday and introduced the idea of bar formulation. I gave you an equation for doing bars, and we were doing a hand calculation. And as we've discussed previously, our FEA process is coming up with a mathematical model of a physical reality. And in that process, we are going to represent the physical reality with nodes and elements and solid models and all of those types of things. And then hopefully we do so in a way that our model tells us something useful about our physical reality. Okay, so obviously that's the whole reason we're doing this, is to learn something, to test something, so that we don't have to build a physical prototype to determine some of the things we might want to know about some structure. Okay? For our airplane, we'd like to know if we have a critical natural frequency in the wings before we build the thing, and then the wings vibrate off the first time it flies. Okay? There's useful things that we can determine that could save us headaches later. So assignment 3 is going to be our first stab at using Solidworks to do an analysis. And I am intentionally doing this a very strange way that you're going to be like, I don't understand why he's doing it this way. Okay? That's on purpose. And so I'm just prefacing that with, as I'm trying to get you to have a little bit of insight as to what the implications are of these different possible ways that I can model something. Okay? So I'm just starting off at the beginning of class today with saying that is, if you don't listen to what I say today, and I'm particularly concerned about the people that are not here today, that are supposedly taking this class that I've never heard from, how are they going to figure out what we're supposed to be doing? So I'm going to reach out to all of them this afternoon and say, hey, you need to be watching these videos if you're not already watching them, okay? So that you understand the point here. So we're going to start today using bars and beams to represent structures. And we're going to keep it really, really, really ridiculously simple and see how well does that solution match to the solution that it should have. Okay, so that's the point. And that's why we're going to start with just beam elements instead of trying to model our structure as accurately as possible. So the reason I'm doing this is, first of all, to introduce you to the different ways you can possibly model something, but also to point out to you that if you just need a quick and dirty number, that I don't want to model my airplane such that it looks exactly like the real airplane. Maybe my quick and dirty model is just a straight line down the axis of the plane and some straight lines out for the wings and the tail. Maybe that's good enough. In case of an airplane, it's probably not. But maybe the situation is good enough. So let's try and model it that way and see how close to the answer that we're looking for do we get. Okay? Now obviously we're going to be doing much simpler models than an entire airplane today, but that's the point, is we're going to model it really, really ridiculously simple and see, are we 100% off? Are we 50% off? Are we 25% off? Are we 10% off? And if we're only 10% off, then why should I spend hours modeling really, really accurate, nice-looking solid models if I can use a straight line to represent it in 10 minutes? Okay? So that's the point of the exercise, and we'll talk more about that as we go through this. Okay? I'm just trying to give you an overview of what we're trying to achieve here. Okay? So we have many different types of elements that we can choose to use to model our structures. Everything that we model is three-dimensional. Okay? If you just start the analysis package in Solidworks and say mesh this and solve it, it is going to use a three-dimensional element formulation as a default. Okay? And you will get an answer, and it will probably be a pretty good answer. The problem is it takes huge amounts of resources to model with three-dimensional elements. And so if we're doing something simple like what most of our assignments are going to be, it's probably not going to make a big difference because what we're doing is so small that you can, make it really accurate, make it really complicated, and it's not really a time premium for you. On the other hand, if you're trying to model that entire airplane, you better understand the types of elements that you're doing, because if you try to model that airplane with solid elements, then you're probably going to create terabytes of files, and it's going to take days or weeks to solve it. Okay? So, we can simplify things all the way down to a one-dimensional element. And a one-dimensional element just has a length associated with it. It's a straight line connecting 2 points. What types of things might I want to model with a one-dimensional element?
You could do any type of beam you'll be loaded, most likely.
Okay.
Yeah, a truss. You could probably get away with a truss.
A truss.
Yeah.
A truss would be a perfect thing to model with a one-dimensional element. We're assuming that the cross-section of the members are not changing down their length, right? Okay. So think about that for a second. I could model, say, the Kennedy Bridge with one-dimensional elements, and my one-dimensional elements would just be the cross-section of whatever those particular pieces are that make up the bridge. Now think about how many pieces are on there. That would still be a lot of pieces if I just use one-dimensional elements. Okay? So a truss would be an obvious thing. A frame, anything that has long pieces that are of constant cross-section could be modeled with one-dimensional elements. Two-dimensional elements are flat plates or shells. So what kind of things would I model with that?
You could do like a shelf.
A shelf?
A shelf.
Okay.
Yeah.
All right, a shelf. tank like a storage tank, right? Has thin walls. Thickness of the tank is not terribly important to the, there's not a lot of variation in stress in the tank through the thickness of the wall. So you can model an entire tank with a shell. Back to the fuselage of this airplane. That's mostly two-dimensional shells that you could wrap around that whole thing to model the airplane. Okay? So two-dimensional plates and shells would be appropriate for modeling things where variation through the thickness is not significant. And then three-dimensional elements would be everything else. Okay? Now let's go back to our bridge example. Could I model the Kennedy Bridge with two-dimensional elements? Sure. Yeah. Good. And so let's just pretend like the Kennedy Bridge is just made up of simple I-beams. Okay? I could represent the bottom flange as a flat plate. I can model the web as a flat plate, and I can model the top flange as a flat plate. Okay? So if I was looking at kind of in a 3D sense, I don't know where I'm going here with this. Let's draw this like this a little bit better. Okay, so there's my I-beam, right? Does that look, it's about right, isn't it? Trying to do an isometric on an I-beam. And so if I was to model this as a single one-dimensional element, then this could be nothing more than the node starts here and it's a straight line going back here to wherever this beam ends, right? Could even do one element. That one element, if it's, we'll talk a little bit more about it today, but if it's a three-dimensional beam that has both bending and axial tension, that each node is going to have 6 degrees of freedom. Okay? So 2 nodes times 6 degrees of freedom, that's 12 degrees of freedom total. We're going to be talking about degrees of freedom repetitively through the semester, so we kind of get, I'm trying to use that as a comparison of the complexity of the different models that we can use. Okay? Now, if I want to use 2D shells to do this same thing, I could do a shell, just a single element that, is this, these are the corners like this. Okay? So there's 1, 2, 3, 4, 5 of those. Now the reality is that if I was going to do this, I'd get horrible answers if I did it that way. Okay, so I really need to break this shell down into smaller pieces. Well, let's just say I did those 5. It would be a horrible model, but let's say I did those 5. Then I have 1, 2, 3, 4, 5, 6, so 12 nodes times 6 degrees of freedom each. What did I say? 12 nodes, 12, so 144 degrees of freedom versus my 12 degrees of freedom that it starts with. Okay? Reality is that would be a horrible model. My single beam element would be pretty good. Okay, but shells like that would not be good, and we'll talk more about why not as we go along. But in reality, I really need to break these into little shells that look like this. And every single one of these is a node and an element. And so I'm probably talking about orders of magnitudes of more complexity by just changing from a one-dimensional element to a two-dimensional element. Okay? And remember, every time we increase degrees of freedom, we're talking about increasing the matrices that we're dealing with, and we're increasing the time that it takes the computer to solve this. Okay, does that make sense? Everybody understand what I'm saying? Okay, now, what if I model the Kennedy Bridge with three-dimensional elements? Okay, general good practice is through a thickness, I need at least 3 elements. So if I'm going to do this with solid elements, I could absolutely do it. But I'm going to have to break up the flange and I'm going to have 3 layers of elements through the flange, in addition to all the little pieces that we broke it down to when we did it with the shell elements. Okay? So we're just talking about a ridiculous number of elements is what I'm trying to say. All right? So millions, possibly even billions of elements times the number of degrees of freedom, and it rapidly gets, can you do it? Absolutely. Do you really want to wade through all that data? Well, there's absolutely no reason to. I mean, model it as a 2-dimensional element, and you're going to get pretty close to the right answer. Now, you're not going to get all the details of the welds of every weld on the bridge. If you wanted to do that, you'd have to model it as 3-dimensional elements. But it would be a hugely inefficient use of your time and computer power to do that. Okay? So that's the point I'm trying to make there, is that let's simplify things to the simplest type of model that gives us good results. And so the common theme as we work through these assignments is, let's try modeling it this way and see how good the results are. So for example, on assignment 3, there's going to be a tapered beam, and you're going to see that tapered beam multiple times through the semester. And we're going to model it different ways. It's the same simple, stupid-ass little tapered beam. Same answer every time, but the point is you're going to see how the different element formulations give you different results, and hopefully we'll see that we're getting closer and closer to an ideal result. So the first one we do tonight is we're going to model that tapered beam as just a single element, a single cross-section, and you're going to get reasonably bad results for that because it's just not a very good model of that beam. Okay? All right. Again, the other different types of elements. So 1D is a line, 2D is either a triangle or a quadrilateral. If we go 3 dimensions, we have tetrahedrals, which are triangular shapes that make up a 3-dimensional object, and we have rectangular prisms. Different FEA software uses different meshing methodologies. It's much easier to split arbitrary shape into triangles than it is to split it up into rectangles. Okay, so you take any shape, and it's mathematically very easy to split it up into triangles. It's not nearly as easy to make rectangles out of it, unless it happens to be a rectangular shape to begin with. Okay, so most cases we'll be dealing with triangular elements, unless SolidWorks has changed significantly. By the way, I was driving, or last night I went to look to try some things in SolidWorks last night and realized that I only had 14 installed on my laptop. And so I didn't get to test 15 because I forgot to install it and didn't think about it until late last night. But assuming that there's no significant changes there, then we're going to see triangles forming when we mesh in SolidWorks.
So we only have 14 on these.
Oh, really?
Yeah, that's what they are here.
Oh, okay. Well, then maybe we're in better shape than I thought. I really thought we had 15 in here. Okay, well, never mind. Then I guess that's going to save me some work reinstalling the software.
Yeah.
Okay, so when we mesh something, if we're using 2D or 3D elements, we should see triangles being meshed because that's what SolidWorks uses. Some other software uses rectangular elements. ANSYS, for example, you can choose to use rectangular elements. I think there's some options. I'll have to go back through and dig through the SolidWorks options. Right now, off the top of my head, it's been long enough that I don't remember if there's a way you can switch on rectangular elements in SolidWorks. So, depending on the software, depending on the options you choose, you will get, you can get different element types. And so part of what we'll be doing is also looking to see through SolidWorks, how do you choose to use the different element types? Okay? So, the nice thing is that SolidWorks tries to do everything for you. okay? And it will try to choose settings for you. I like to take pictures. One of my hobbies is photography, right? And if you've used a camera in the last 15 years, there is an automatic setting that you put on the camera, and it figures out what aperture, which shutter speed, what white balance to use. It does all of that for you, and those automatic settings have gotten sophisticated enough that you can take some pretty damn good pictures just leaving it on the automatic settings. However, if you want to have a little bit of artistic control, if you want to, take pictures in a situation that the autofocus and the aperture settings just don't do a real good job, then it's nice to be able to manually control those. And so if you have a more sophisticated camera, you can change it to manual settings, and you can tweak any of those things to get the effect that you want. Okay? So part of my goal here too is that you understand what all those manual settings are, so that if you need to tweak the defaults, you understand the implications of tweaking the defaults in SolidWorks. Because quite honestly, if it was just to let SolidWorks do everything for us, this could be a 1-week class and we could be done already. Okay? If you're just going to let SolidWorks make all your decisions for you, then there's obviously not a whole lot that I can help you with. Click there, you're done. So the point is that we're going to hopefully learn a little bit more about what these settings mean, so that you can tweak those so that you get better results out of your analysis. Or even just understand what is the result that you're getting out of your analysis. Okay? All right. One other thing I wanted to mention real quick. Think about using symmetry to save yourself some work. And we'll talk more about this later, but I wanted to bring it up now. There is absolutely no reason to model an entire structure if I can simplify it by dividing it in half. Okay? As long as our loads are symmetrical, as long as our geometry is symmetrical, then you can model half the structure, and you tell SolidWorks this is a boundary of symmetry. You apply symmetry constraints to it, and it will then simplify your life as far as how you have to model it, and it will simplify it as far as the geometry you have to create. Okay, I'll purposely give you an assignment where you should do that later. We'll investigate that in more detail, but I just wanted to mention that today, something for you to keep in mind as a task. Okay, so Tuesday we talked about bar elements. We talked that bar elements have forces that are in line with the element, either compression or tension, and they have 1 degree of freedom at each end, which is a movement in the axial direction of each end. Okay? So we said that each element has 2 degrees of freedom. So we have stiffness matrices that are 2 by 2, corresponding to the degrees of freedom, and we went all over all this on Tuesday. Okay? Now, this only works if we're wanting to do truss elements. In a more general case where we have bending, we need to have the capability for forces to be perpendicular to the element, and we have to have degrees of freedom that are perpendicular. Okay, so that brings up a simple beam element. So this is the simplest beam formulation. This has displacements that are perpendicular to the axis of the element, and it has rotations. Okay? So the simplest beam element, each end can displace perpendicular to the axis, and each end can have a rotation corresponding to it. For beam elements, we have to have those rotations involved too, because think about a simple cantilever beam. I put a force down, we're going to have a displacement down here at the end, right? We're going to have a displacement delta. Okay? So I have some displacement. What else happens to this beam? Rotates a little bit, right? So I have to have some rotational degrees of freedom. If I think about back here at the wall, not only does this have to be held up with a force, it also has to be prevented from rotating with a moment. Right? So I can't have a beam element that doesn't have the rotations. So in order for this to be statically determinate, I have to have those rotational degrees of freedoms as well as the displacement degrees of freedom. Okay, so the simplest beam element has this. What this doesn't have is axial capability. So you can't use this element formulation in a truss, because this element does not have the ability to handle loads that are down its axis. So this formulation works for cantilever beams. It does not work for trusses. But trying to keep things as simple as possible, if you're only dealing with bending, then you could use an element formulation like this. Okay? So this is what the stiffness matrix looks like for that beam element that we saw on the previous page. Notice now I have 4 degrees of freedom. I have Y degrees of freedom and I have rotations degrees of freedom. Because I have 4 degrees of freedom, the stiffness matrix is a 4 by 4. Okay, so we got 4 by 4. If you look at this, the EI over L squared, the EI is over L cubed. It looks a whole lot like the formula that we were using in strength of materials for deflection of a beam. I think it's PL cubed over 3EI is one of the ones for a cantilever beam with a force on the end. Okay, so you see the EIs and the L's just like that equation has. Just like back here, we had the EAs over L's for the bar bending. Okay? Now I'm not going to go through how do you come up with this. I'm just showing you that this is what it looks like. My point being, showing you as we get more and more degrees of freedom, these matrices get huge. So this only does bending, it does not do tension and compression. Thinking about that, I'd probably prefer to have an element formulation that has both bending and tension and compression, right? That would be ideal. So I want to create what I'm calling a 2D beam that has the combination of the bar element, which is the 2 axial forces, and the beam element, which is the 2 transverse forces plus the 2 moments. So how many degrees of freedom is that? 2, 4, 6, that's 6 degrees of freedom. How big is the stiffness matrix going to be for one element? 6 by 6. Okay? So it looks like that. I've got my 6 degrees of freedom. I have 6 by 6 matrix. If you look at this really carefully, you see this part is just from this corner here. All right? And then this is the AE over L that we used in the stiffness matrix of the first one. So this looks horribly complicated, but it's not really. Okay, it's just putting the right pieces in the right spots so that when you multiply it out, it hits the right degree of freedom. Okay, so this is a 6 by 6 that represents one element in 2D. So how many elements are in the Kennedy bridge? Every single one of them has the stiffness matrix piled on top, and so you end up with a giant matrix that is tens of thousands or even millions by tens of thousands by millions. Okay? And that's why I said previously that this is not a realistic thing to do until you have computers to crunch all this math for you. It's a pain in the ass enough just to invert a 3 by 3 matrix. Can you imagine inverting something that's 10,000 elements? Okay? It's not going to happen. then you do some kind of silly algebraic error in the middle, you know, and you screw the whole thing up. I mean, it's, you know, that's why we have computers that do this for us, is because there's so many calculations. Okay, so this previous matrix that we just looked at was two-dimensional only. If I'm going to do the Kennedy bridge, I really need a three-dimensional element. Okay, so then that adds in additional degrees of freedom. We still have the two axial forces. We need to have four transverse forces. Okay, so here is an element, 3 dimensions. We have, this is the axial force, the red one. If we're going to be in 3 dimensions, we need bending in 2 perpendicular directions at each end, so that's the 4 transverse forces. And then we need 6 moments. And if you guys remember back to statics, remember we were doing 3-dimensional problems. You had, 6 degrees of freedom, 3 forces, 3 moments, and you had to solve the equations of equilibrium for all those. Okay, so you've kind of seen this kind of stuff before. Okay, so a 3-dimensional beam, sometimes called a space beam, has 6 degrees of freedom at each end. You have 2 ends, so that's 12 degrees of freedom total in the matrix, in the for that single element. And I didn't write it out. I don't think I put it. No, I didn't. Okay, I didn't write it all out for you, but that would be a 12 by 12 matrix for just the stiffness matrix for one element. Okay? So we're okay with that. Now, I'm not asking you to memorize these stiffness matrices. Okay, but I want you to have some concept of what they look like. And that's why I've put them in here on the slides. Now, I will expect you to have memorized how many degrees of freedom does a space beam have, and what are they. Okay, so you need to understand those differences. Know what a beam is, or what a bar is. A bar just has 2 degrees of freedom, which is the axial at each end. A 2D beam without axial loads has 4 degrees of freedom. 2D beam with all has 6, and then a 3D beam has 12. Okay, so you should know the differences between the two, so that if that's a test question, you should know what those are. Okay. So a little bit more theory, and then we'll talk specifically about the assignment. We looked at this already. The deflection of a bar just from axial tension and compression is FL over EA. Here is the tapered beam that we're going to be looking at. Okay? And our tapered beam has a length, I think I said it's 50 inches on the assignment. It tapers from L over 5 to L over 50. So if this is 50 inches long, then this is 10 inches on this end, and it goes down to 1 inch on this end. It is 1 inch thick. So that's our geometry that we're talking about here. Okay? Now, I didn't change my graphic here. In this case, we're talking about tension and compression. So my arrow here really should be pulling that way. Okay, so this equation here is for axial tension and compression. Remember that on this slide, this A is constant down its length, right? Okay, well, we go to a tapered beam now, and this A is no longer constant. Okay, it's a function of the length. So it is, in this specific case, it's 10 inches by 1 inch, so it's 10 square inches at this end, and it tapers down to 1 square inch at that end. So if I'm going to solve for what is the deflection of this tapered beam, then it becomes an integral from 0 to L of f dx over EA, or E times A of x, where A of x is a function of the length down the beam. Okay, this is a calculus problem. And we can come up with an expression that relates the cross-sectional area to the length, and we can integrate that, and we can plug in, and you could solve for what is the deflection using calculus. Okay? What FEA does is breaks that tapered beam up into small sections of constant area. And depending on how many times I want to break it up, I can get closer and closer and closer to that calculus answer. Okay? So in this case, I have broken that area up into bunches of little areas that visually look a whole lot like a tapered beam. What is the simplest way I could analyze that tapered beam? By breaking it down into areas of constant cross-section.
You do 3 beams, right? Yeah. 50.
Okay. Here's my tapered beam. What would be the simplest thing of constant cross-section that I could break it down into?
One section.
Just one piece, right? And what would I do? What would that piece look like?
Just a big rectangle.
It would look like a big rectangle. And I could do a big rectangle that looks like this. And if I modeled it that way, what would be the results? My answer would be bigger, close to, or smaller than the true answer.
Smaller.
I heard both bigger and smaller, so.
Well, I don't know which
Well,
one
it's
you're
not
gonna
gonna move as much.
Okay.
Yeah,
So I'm pulling on it this way, and I'm modeling it with this rectangle. If I do that, I am overestimating the amount of material here, right?
Yeah.
And since I'm overestimating the amount of material, my answer is going to be, my deflection is going to be smaller than it should be, right? But I could use that to establish an upper bound, kind of like as a best case scenario kind of thing. It would be actually a lower bound, right? Okay, what's the other way I can model this?
You could go midway from the.
Okay, well that would probably be the best.
Yeah.
What would be the other worst way to do it? Model it as this rectangle, right? And when I model it as that rectangle, my deflection is going to be too big, and that would give me the upper bound on what the deflection would have to be, right? Okay? Or as Jake, I think, started to say, I could use the average width and draw a rectangle that is the average width of the whole thing, right? And that would probably get us closest to what the right answer would be, right? So if it's 10 inches wide at this end and it's 1 inch wide at this end, then the average width would be 5.5, right? 11 divided by 2 would be 5.5, so the average width would be 5.5 by 1 inch thick. Okay? Do I understand that? Okay? So that would be the simplest thing, would be just a single rectangle that is average width. If I wanted to get a little bit better answer, I could maybe divide it into 2 elements. Okay? So split it in the middle. And I could do one element that is the average of the thicker part. And I could do another element that is the average of the thinner part. Is that going to get me closer to the true answer? It should, right? I can take this a little bit further. I can divide it into 4 pieces. So here's the middle. Okay, I can divide it into 4 pieces where each one is the average of the thickness in that segment. Is that going to get me closer? And so forth. Okay? So throughout this semester, we're going to be talking about mesh refinement. Mesh refinement is making these pieces smaller and smaller and smaller to get closer and closer and closer to the correct answer. The trade-off is the smaller I make these, the more calculations I have to do, and the longer it takes perhaps to come to a solution. In our case, our models are going to be simple enough, you're probably not going to notice the difference in time. But hopefully we'll see the difference in, is our answer converging on the correct answer? Okay? So that's what mesh refinement is, and this is just showing just a more extreme case of this. And at some point, this becomes so refined that we are nearly perfectly modeling the exact taper of that beam. Okay? All right. We can also look at this tapered beam with a straight beam with bending. So the equation for bending is PL cubed over 3EI, as we talked about earlier. If I want to apply that to a tapered beam, it becomes a calculus problem. Now my I is a function of the location down the length. And so it's fx squared dx over EI, where EIx, where I is a function of x. Okay, I can integrate that and come up with an exact solution. I can apply finite elements to that, break it into smaller and smaller pieces, and approximate that exact solution. And then I'm also going to show you something here that is really useful. And this book is called Works, Formulas for Stress and Strain. It was originally written by some guy named Rourke. That's why his name's on it. Okay? And then, I don't know exactly, but I'm assuming he died at some point. And it's now being republished, edited by, in this case, these two guys. Young and Budnius, I guess. Okay? So this book used to be called Formulas for Stress and Strain, and it was written by Rourke. Now it's Rourke's Formula for Stress and Strain, edited by these two guys. I assume they're guys. I don't know for sure that they're even guys. Okay? So the reason I'm showing you this book is an entire book on the tables that are in the back of your 211 book. Okay, so think about your beam bending formulas and your axial loading formulas and all that are back in the back of your 211 book. Well, this is that on steroids. Okay, so when I was working in industry, I kept a copy of Rourke's book on my desk because I was constantly coming up with situations that were close but not exactly to the formulas that are in the back of the 211 book. For example, there's in here there's a section on circular plates. You have a circular plate and you have a load in the center of the plate. What is the deflection on that plate? Well, that's not in the back of the 211 book, but it is in here. Okay, so this is a powerful tool if you're doing structural analysis. This has tons and tons of equations for you that help you come up with a calculation of what kind of deflections and what kind of stresses should you expect to find under some particular loading circumstance. Okay, so I've got this book here for you. You're welcome to borrow it if you want to use it. If you do this kind of thing, or think you might do this kind of thing in the future, I would highly recommend that you buy that book. It's really useful if you need to find these calculations. So, looking at this is what one of these tables looks like. And so this is a beam bending, left end free, right end fixed, a cantilever. In the back of your 211 book, you have a cantilever beam equation, but the force is always on the end of the cantilever. So this is a little bit more general case in that if the force is not on the end. Okay? If it is on the end, then A is equal to 0, and you just plug into these equations and A is equal to 0. And if you do that, you'll see that these equations simplify down to the equation that you're familiar with in the back of the 211 book. Okay? So this equation is just going to be the PL cubed over 3EI. Well, look at this equation right here. Okay, so I'm using W here instead of P. Go back on this equation, I had P, right? That's the force. This one I have W. And then if A is equal to 0, these two terms are going to be 0, right? So this says W times 2 times L cubed. And then that's over 6EI. Well, the 2 over 6, that's 1/3. So this becomes WL cubed over 3EI. And if I replace the W with the P, then I have this exact equation, right? Okay? So this equation is just a little more generic in that I can have it where my force is not on the very end of the beam. But this is basically the equation that comes out of your 211 book. And then there are tables that give you correction factors that if you have a tapered beam. So your back of your 211 book definitely doesn't have an equation for a tapered beam. But Brooks has, if your beam has a taper to it, it has correction factors. This is not going to give you the exact result, but it gives you an approximation of what would be the theoretical result for your tapered beam. So, this IA over IB, IB over IA. IB would be the end on the wall, and IA would be the end where it's where the load is applied. Okay, so looking back at our tapered beam, we're going from 10 inches to 1 inch. So for a rectangular cross section that is 10 inches by 1 inch, what is the formula for I? You guys remember this from 211, right?
Isn't it like base times height cubed over 12 or something?
Yep. So this is 112, I do it 112 BH cubed. Okay? So the moment of inertia of a rectangular section, this is a rectangle. The moment of inertia of a rectangular section is 112 BH cubed, this would be IB because it's by the wall, is 112 BH cubed. So that's 112 10 times 1 cubed. IA is at the small end. Same equation, 112 BH cubed. This time the B is just 1. So that's 112 1 times 1 cubed. So IB over IA is what ratio? The 1/12 is the same, the 1 cubed is the same, so it's 10 to 1, right? So my ratio is just 10. So on my chart here, my IB divided by IA value would be 10, which unfortunately happens to be off the end of my chart. Okay, a life lesson. You're not always going to find a table that matches your situation. So what are we going to do in that case? Write my report, sorry, Professor Dews, the answer doesn't exist, so I can't answer your question.
Extrapolate.
Huh?
Extrapolate.
Extrapolate, right? So the easiest thing to do would just be plot these factors for 0.25, 0.52, and 4, and 8. Figure out what 10 looks like. On here it's 0.171. I think if you extrapolate it out, it's like 0.15 or something. Okay? So what do these factors mean? These factors are what you multiply the displacement by in order to get the correct answer for that tapered beam. So if I had used a constant cross section for my beam, and I came out with 1 inch of deflection, then my true deflection would be 0.171 of that, or 0.15, whatever that extrapolates to, times that 1 inch. Okay, does that make sense? So use the the equation here, the PL cubed over 3EI, and then you multiply that by the correction factor for the tapered beam. And that gives you the actual deflection. Okay, what I do I use? Well, if I think about that, the factor is 0.171. So I'm probably going to need to use the big, I'm sorry, I'm going to have to use the small I, IA, in this equation, right? Because the IA is going to give me way too big of a deflection, then I'm multiplying that by 0.171, which then brings it down to the right value. Okay, so using this table, in this equation, you'd use the IA value, you multiply it by the 1.15, whatever it extrapolates to, and then that gives you the correct answer for the tapered beam problem with a hand calculation. Okay, so I'm showing this to you because I want you to understand how do I go from a hand calculation to something that I'm going to calculate in Solidworks. Okay, so any questions about that?
And have us do one on the assignment.
Yes.
Very good.
So you're going to be doing this tapered beam, and you need to do this hand calculation, and I've just told you exactly how to do it. Okay? Now later on, I'm going to expect you to know how to do it. Okay, but for this one, I've just told you, this is how you do it. This is where the equations are. This is how you calculate your hand calculation. And if we have troubles with that, then we'll come back and revisit it. That's what I'm here for. Okay? So there's all the equations for it. You should come up with a value for a hand calculation. If you want, you can absolutely do the calculus. Do the integration calculated that way, and you'll get a better answer because Rourke's tables are an approximation. So you can do the calculus if you want to. I haven't talked about it, but I just, just a random thought I just had is MathCAD there's a free version of MathCAD, and it is basically a word processor that does math for you. Okay, so something you might consider. What I use for my solutions is MathCAD. So what you do with MathCAD is you program in, and actually it'll even do the calculus for you if you want to. Okay, but you program in this equation. You tell it, here is the equation. You tell it what is, you say P equals, and you type in P. L equals, you type in L. E equals, type in the value for that. I equals, you type in the value for that. You write the equation, and down here you say deflection equals, and it does the math for you. Okay? Now the reason that's useful is because the reason I use it for my solutions is then every semester when I change these problems slightly, then I just type in the new numbers for P and L and E, and then it updates the correct answer, and I don't have to go back through and type it in my calculator again. Okay? So something you might consider using is MathCAD. If you want to buy the full version, it's expensive, but they have a free version that is very useful too. And I would highly recommend it for doing these type of calculations. Okay? And if you need some help with MathCAD, I'll be happy to help you start. It's one of those things where you got to kind of have to learn how to do it. To do this equal sign, you have to actually use a colon instead of the equal sign. Okay? So there's a couple little tweaks you have to do. If you're interested in doing it, I'll be happy to help you with it. But I would highly recommend it if you'd like to start learning to use that to do some of these calculations. Any calculation you think you're going to have to revisit in the future, if you do it in MathCAD the first time, then you can just keep reusing it later on. And I'm telling you right now, we're going to do this tapered beam calculation a bunch of times this semester. So it might be worthwhile learning how to do that, and you can utilize it later and just repeat the work again. Okay. So the tapered beam problem, I'm gonna give you the assignment in just a second. The other part of the assignment is we're gonna do a truss in Solidworks. Okay, and so I have some slides up here. If you model your truss in Solidworks and you put fixed constraints down here and you put a load down here, you're going to get rigid body motion. Because if we think about this for a second, my truss elements do not have rotational degrees of freedom. Okay? So even though I fixed this into the truss, this thing can warp in and out of the page. Or another way you can think of this is sort of like a gate. It can, you know, this is the pole of the gate, and this whole thing can swing around that pole. There's nothing to prevent that. And so you're going to get mathematical problems. Okay, so something you have to be careful of, something you're going to have to get used to is thinking about how does Solidworks view that problem versus the way you view that problem. We're pretty comfortable with thinking this is a two-dimensional problem. It doesn't warp out of the page or out of the screen, or however you want to think of that. But in reality, you just modeled it as a three-dimensional thing, and it's going to move in and out of the page because there's nothing to prevent it from doing so. So the second part of the assignment on your truss, you're going to have to put constraints on the nodes that are perpendicular to the plane of the truss to keep it from coming out of the plane. Okay, so that's a little hint for the second part of the assignment. Okay, so I printed out the assignment this time. If you haven't already looked at it, it's also posted online. Okay? So, there's two problems here. It says, solve the following problems using SolidWorks and compare to a hand solution. What does that mean?
You do a hand calculation and use SolidWorks.
Okay, you do a hand calculation, you do a SolidWorks calculation, and then what are you going to do with those two numbers? You're going to calculate a percent difference. Okay? So when I'm looking at your assignments, I should see a hand calculation and a value. I should see SolidWorks and a value. And I should see a comparison of the two as to how much percent difference those two are. Okay? Does everybody understand that? All right, so here's my tapered beam. It says, create a finite element model using elements of constant cross-section using beam elements. Use 1, 2, 4, and 8 elements of approximately equal length to approximate the tapered beam. Okay, so this is exactly what I drew on the board earlier. If I'm going to represent this beam as one element with a constant cross-section, then that element is 5.5 inches wide by 1 inch tall, and it is 50 inches long. Do that analysis and see what SolidWorks tells you the answer is. Then do two elements, each of them 25 inches long, and one of them is going to be 7 something, what, the average of 10 and 5.5, so that's 15.5, so that would be, what, 7.75? And then the other one would be the average of 5.5 and 1, which would be 6.5, so that'd be 3.25. Okay, see how, where we're going with that? Then do 4 and then do 8. Now there's a note there, is that SolidWorks, the beam cannot be shorter than it is wide. So as we get down to the 8 elements one, you're going to have to tweak the lengths of the pieces a little bit so that it doesn't end up shorter than it is wide, because SolidWorks will not be able to figure that out for you. Okay? So what that means is they can't be 8 equally spaced pieces. You're going to have them with different lengths to get those 8 in there. And however you want to figure that out is fine. But we just need to have 8 elements. Okay, we're using beam elements, beam type elements. So the other thing that I need to show you is the way that SolidWorks does beam elements. Okay, so everybody listen to me. Do not draw a 3D solid model of a tapered beam in Solidworks. Okay, we'll do that later. This is where I'm artificially forcing you to do it a really simple way. And so your model of this beam is just a single straight line in Solidworks. So the solid modeling part of this will take you exactly like 10 seconds. Okay, do not draw a tapered beam. So in SolidWorks, you're going to go and you're going to create a sketch. And so if I am doing my single beam element for my tapered beam, you're going to create a sketch that has a line that is 50 inches long. Okay? And that's all you have to draw in SolidWorks.
Just in a sketch.
Just in a sketch. Okay? Now, to get it to do beam elements, you have to use the weldments capability in SolidWorks. Okay? Have you guys used that before? Okay? So, you draw a sketch of a line. Maybe the easiest just to fire up SolidWorks here. Okay, so to do this, all we need to do is create a line. I'm just going to create an arbitrary line in some direction. Okay? And then you can use the weldments. Go up here, insert weldments, and it has a structural member tool. Okay? Select that, and it will say select a line. And so you select the line that you want to use, and then you have to tell it what its geometry is. Okay? So I will show you there's built-in angle irons, pipes, tubes, things like that. There's a rectangular tube. What size is it? Just pick one here, and it creates an extruded piece like this. Okay? Everybody see that? So what SolidWorks is going to do, your model is just the line, and then SolidWorks is going to use the area and moment of inertia properties of this tube to figure out how does it deflect when you go to do the analysis part of this. Okay? So by defining it with this cross-section, that is to establish the cross-sectional area, the moment of inertia, and all those things that SolidWorks is going to need to do this. So, for your tapered beam, what are you going to select so that you have the cross-section that you want for this tapered beam? Go back and look at these options. It has a rectangular tube, it has angle iron, it has C-channel, it has pipe. where does it say Professor Dews's tapered beam sections?
I think you download that, right?
Okay? It doesn't. So what you have to do is we have to define our own. Okay? So what you're also going to have to do, so that's just how to use the weldments part. Okay? To define your own cross-section, you go and just create a new file. Or I'm going to close this out first. Check mark that. Sorry, change the options here. Okay, so there's my structural member. If I wanted to use something other than the ones that are built-in profiles, then you can do File, New, create a sketch. Okay, so we want to create a sketch. Sketch, choose front plane, and then in our case, let's say we're going to do the first one, and we want a rectangle, and I'm not going to dimension it. No, I guess we can. So we want it to be 1 inch by, what did we say, 7.5? Oh, no, it was 5.5, wasn't it? Okay. So there's my sketch, exit my sketch. So there is, I've created my cross section. Okay? Now I need to save this so that it comes up in the options for me for my structural members. So I want to save this as, so do File, Save As, and we want to save it as, click the types, we want to save it as a library feature part. That's the second one there. So it's SLDFP, or LF, SLDLFP is the file type. We want to save it as that, and then where do we want to save it? If you're doing the work here, you have to be very, very careful because as soon as you log off, it's going to erase any files that you save on the C drive, right? So this becomes easier if you do this on your own computer where it will keep all your files. But the place you want to save this is the same place where all those other files are. And so they're on the C drive. Go to Program Files. And then SolidWorks. Or actually SolidWorks Corp, I guess. SolidWorks. And then under Language, so LANG. Then English. And then weldment profiles. And I'm just going to save it under ANSI ints, and I'm going to save it, you can create a new folder. So this is going to be dues. Put it in that new folder, and I'm going to call it Part 2. And I'm going to save it. And now hopefully if I did everything right, I go back here, do File, Weldments, or Insert, Weldments, Structural Member, under ANSI Inch. There is now a Dues folder, and then there should be a size that is Part 2. Okay? And then you can click that, and then it should create your cross-section for you. Okay, so you're going to have to create the various cross-sections, and then use that to model these pieces. You're not going to find these sizes as defaults in SolidWorks. Okay? So down here at the bottom, this truss, we're going to consider the cases of the cross-section being 5 by 5, 15 by 15, and 30 by 30. So you're gonna need to create a cross-section that's 5 by 5, just rectangular. It's a cross-section that's 15 by 15, and a cross-section that's 30 by 30 to do the second part. Okay? Last little thing I guess I should show you real quick is once you have a solid model, I'm going to cancel this. It looks like simulation is already loaded on here. If you install this at home and simulation is not loaded by default, if you go to Office Products, then you click on SolidWorks Simulation, it will load that module for you. If you've already got the tab, then you can just go to Simulation. Okay? We're going to do this. You don't need to do the advisor. When you're ready to solve this, choose New Study. And it will come up and it'll ask you what kind of study do you want. And we're just doing a static study. So just choose static. Say OK. And then it will be ready for you. There's buttons up here. Okay, so remember our process. We have to apply loads. So there is a button up here, external loads, and it has a bunch of different types of loads you can apply. There's a button up here for fixtures. So you will have to apply your constraints. So use that button to fix one end, use the forces to put a force on the end as appropriate. And when you do those options, you will see you can specify which direction the force is. And there's lots of options, and I'll let you play around and click with those. I think it's pretty self-explanatory. Once you have that, you have to apply a material. And you can actually, if you look at this, you can kind of just step your way across, okay? Apply the material. It comes up. I didn't really give you I didn't specify exactly on here, so just assume that it's steel. So you can just choose the steel from the materials. You can just use the defaults. Apply constraints, apply loads, and then you click run, and it will solve it, and then you click on the results, and you can figure out what your displacement is at the end. Okay? So that's a really brief explanation of how to run that. Being kind of vague because I'd like you to just sit there and click around. I think this is a case where you figuring it out on your own might be a little bit more instructive than if I give you a recipe. I'd like you to understand what's going on, so I'll let you click around on that a little bit.
So you
Okay?
just want to use like plain carbon steel for material, or?
Yeah, just the plain default carbon steel is fine.
Okay.
Okay? Now, if you bought these books, you will find in here, it will tell you exactly how to click through to do a static analysis. Okay? Now, I told you to buy the 15 version because I thought we had 15s in here, so hopefully they're, huh?
That's what the student version
Is that what the student is?
It won't let you download 14.
Okay. Okay. All right, so we might have a little bit of versions. In recent years, I've not seen significant changes in the way this happens. So I think regardless of which version we've got, I think we'll be pretty close. But in this book, it has, if you really like the step-by-step cookbook instructions, then look in here and it will step you through how to do the analysis. Okay? Something to consider is I don't know how compatible the two versions are. So if you're doing this at home on your laptop using 15, I'm not sure if you can bring those files in here and use it on 14. I'm guessing you probably can't. So think about that. If you're going to work in here, you're going to be using 14 because that apparently is what's installed. Do we have both versions installed maybe? No. Okay.
You can take 14 to 15, but not, you can't go backwards.
Okay.
Go old and then you're not doing
Okay. So keep that in mind, is if you start here, I guess you could go home and continue. But if you're at home and then you come in here for class and you don't bring your computer with you, if you're doing it like on a desktop, then you can't use your files here. So that's kind of a pain in the ass, and I'm sorry about that, but I don't know there's a whole lot I can do about it at this point. Okay? Trying to understand what we're supposed to be doing? All right. I will be here for questions, so as they come up, let me know, and I'll do my best to help you with that. Okay? All right. Not planning on a lecture on Tuesday. Tuesday is work time. If you want to come in here and work, I'll be here. Next lecture will be on Thursday. Okay? All right. Have a nice weekend, and I'll see you guys next week.